Hi, today I want to show you one of RidgeRun's latest streaming solutions in action, Gst WebRTC, and how it can help you and your company easily build a flexible and scalable multimedia project that supports WebRTC streaming. If you're watching this video, chances are that you are developing or planning to develop a streaming product of your own, or simply you were researching about the next big thing in regards to streaming protocols and found that WebRTC is definitely one of them. On the other hand, you may also be considering already GStreamer as the multimedia framework for your project. If you are not familiar with GStreamer, I encourage you to check our developers wiki page, Why RidgeRun Loves GStreamer. In that wiki, you'll find comments about real use cases we solved for customers and how GStreamer made it not just possible, but simple, modular, and scalable as well. Gst WebRTC is a GStreamer plugin containing two elements, WebRTC source and WebRTC sync. By linking them into your existing pipelines, you can turn them into WebRTC compliant endpoints. Let's start by inspecting the WebRTC source element. The first thing to notice is that it exposes two path templates, one for video and one for audio. Now I'm scrolling down to the properties section, but I'm just going to focus on the ones related to WebRTC. The first pair of properties configure the signaler. You may choose to use an internal built-in signaler, or you may choose to use your own external custom signaler. Among the list of internal signalers, we only support OpenWebRTC. This list is expected to grow as the project evolves. As you may expect, each signaler will expose a unique set of properties, and these properties will vary according to the selected signaler. To access these properties, we use the special proxy notation. We are going to see this in detail later in this video. On the other hand, if you choose to implement your own signaler object, you may refer to the Signaler's Developer's Guide for information on how to extend the base signaler. The next pair of properties allow you to customize the stone and torrent server to use in order to perform NAT traversal. The certificate property allows you to configure a specific certificate, otherwise a random one will be generated for you. The start call property tells the pipeline whether or not to start the call when everything is ready to go. If set to false, the pipeline will just stand by and wait for the peer to start the call. Finally, the RTCP MUX tells the RTP and RTCP streams to multiplex into a single port. If set to false, RTP and RTCP will travel in different ports each. Whenever possible, Gst WebRTC tries to multiplex these streams. If we study WebRTC sync, you'll notice that it has the same set of properties and exposes the same set of path templates, but with opposite directions. Now, let's put Gst WebRTC to action. The plugin was designed in a way such that both WebRTC source and WebRTC sync behave like regular source and sync elements. Let's consider the simplest pipeline possible. On the sender pipeline, I use video test source as my source element. Then I encode these buffers using the H.264 encoder. Later, I payload these encoded buffers using the H.264 payloader. Finally, I push these resulting buffers into the video path of the WebRTC sync. Next, I configure the WebRTC sync element. I'm telling it not to start the call automatically, instead to wait for the peer to start the call. Finally, I configure the OpenWebRTC signaler. I'm configuring the server URL with RidgeRun's hosted OpenWebRTC signaler. You can access this signaler in order to test out Gst WebRTC. Finally, I'm using RidgeRun as the session ID. On the receiver pipeline, first I configure the WebRTC source element. On this side, I'm telling it to start the call automatically. Then I configure the OpenWebRTC signaler the same way as I did before. Next, I depayload the incoming buffers using the H264 depayloader. And finally, I decode these frames using the H264 decoder. At this point, both pipelines will start using OpenWebRTC signaler in order to negotiate media capabilities and share ICE candidates in order to perform NAT traversal. The call will start when both pipelines are ready. There you go. This message was printed because I'm using the evaluation version of Gst WebRTC. If you would like to try it for yourself, contact us via inquiries@ridgerun.com and we will prepare the binaries for your preferred platform. Now, if we would like to add audio to the equation, it's just a matter of adding the audio branch to the WebRTC sync. As you can see, I've just added the audio test source configured to produce ticks instead of a constant wave. I've used the Opus encoder and the respective payloader and pushed those buffers into the audio pad. Similarly, I've requested the audio pad from the WebRTC source, then used the Opus depayloader and decoder and pushed those buffers into the audio sync. As expected, the video test source shows up along with the audio test source. Additionally, Gst WebRTC endpoints may communicate with other WebRTC compliant endpoints. For example, I'm going to use Gst WebRTC sync in order to communicate with OpenWebRTC demo web page. The pipeline is similar to the one used before, except that this time I'm using VP8 to encode the stream. As you can see, I'm configuring the pipeline to automatically start the call. Now, if I go to the OpenWebRTC demo web page that we have hosted on our server for you to try and connect to the RidgeRun session, I should start receiving the video test source. Note that pressing the call button was not necessary since the pipeline was configured to start automatically the call. Now, if there are other WebRTC solutions out there, why did we decide to develop our own? The keywords are flexibility and simplicity. Consider, for example, that you would like to stream the contents of a video file rather than using a conventional camera or a video test source as we did earlier. This is not a trivial task for existing solutions, if not impossible. This is not the case, however, for Gst WebRTC. You just need to come up with the appropriate pipeline. In this example, I'm using a file source pointing to the appropriate location. Then I'm using QuickTime to demux the stream and taking out the video buffers and pushing them through the payloader and finally to the video pad of WebRTC sync. Similarly, I'm taking out the audio buffers, transcoding them, payloading them and pushing them to the audio pad of WebRTC sync. The receiver pipeline is similar to the one we used before, so when this call is ready, I should see the contents of the video file and the audio fully synchronized. There you go. One detail worth mentioning is that I was able to take out the H.264 frames directly from the file and pushing them directly into the stream. I did not have the need to transcode them in order to push them to the WebRTC element. This is extremely valuable when working on mobile devices with limited resources and where battery life is of extreme importance. Finally, I would like to point you to the official project's documentation. It is hosted in our developers wiki pages. If you type Gst WebRTC, the page should come out as the first results of the query. The documentation is divided as the following. First, we have WebRTC Basics that covers basic topics about WebRTC itself. Then we have Introduction to RidgeRun's Gst WebRTC, which covers most of the topics that I already covered in this video. Then we have the release notes. Then we have Getting Started with Gst WebRTC, which is a quick configure, build and installation guide. Next, we have a collection of pipelines for different platforms for you to test. We have pipelines for NVIDIA's TX1, NVIDIA's TK1, IMX6 and much more other platforms. Finally, we have the wiki page that I mentioned earlier, a Gst WebRTC Signaler Developers Guide. For more information, please write us at inquiries@ridgerun.com and ask for more details and for the evaluation binaries for your preferred platform. Thanks for watching Hands on Gst WebRTC.